All right, hey guys, today we're going to talk about the quantum mechanical model, which includes electron configuration and orbital diagrams, which we did both on the POGIL, okay? Please make sure you have your periodic table out if you're following along at home. All right, so we are going to talk about orbitals, which we did discuss in the POGIL. So most of this at the beginning, we're not writing anything, we're just kind of taking it in. Sorry. All right, so we know that electrons don't behave like other things. Electrons are like photons. They kind of act like light. All right, so as we're going through, we know that you cannot predict the exact location of a baseball as we throw a baseball, but you can predict a probability map that looks something like this. Okay. Electrons are kind of the same. We are going to talk about the principal quantum number, which tells us which shell it is. Remember, the shells in the Bohr model were labeled n equals 1, n equals 2, n equals 3. So we'll talk about that principal quantum number next time, but that just means the shell. Ooh, sorry. Okay. I need to use my mouse because I'm touching my mouse pad on my computer. All right, we already talked about ground state. That's the lowest energy state once they drop back down. We've already talked about excited state. That's when they gain energy and they jump up to a different shell. Here are our shells. Remember, 1 is the lowest energy level, where 7 will be the highest, although we don't normally go that high. The highest you saw in the POGIL was 3, but hopefully in the Edpuzzle you saw a bit more. Subshells, those are the S, P, D, and F. We did label them last class. So again, please make sure you have out your periodic table. We will need to be able to use that. Okay, all the sublevels do have their own shapes. S is a sphere. I would go ahead and write that down, that the S sublevel is a spherical shape. Okay. And remember, I told you that the principal quantum number, is the shell. That is the same as like the row on the periodic table. So on row 1, we only have S. On row 2, we have S and P. Really, on row 3, we only have S and P. We'll get to the D sublevel in just a little bit. And on row 4, again, we'll get to the F in a little longer, okay? But on row 4, you can see we have S, P, and D easily. So this is just showing that 1s will be the smallest because it's closest to the nucleus, where 2s will be bigger because it's the second shell, and 1s has to fit inside of it. So if they're asking about electrons and how close they are to the nucleus, the lower the the principal quantum number, the closer they're going to be to that nucleus. P, they kind of have lobe shapes, or dumbbell, we kind of call them. I'm not going to ask you to tell me this one. I do need you to know that S is spherical. Every once in a while we'll draw these, but very rarely. P does have 3 orbitals. They are in the x-plane, the y-plane, and the z-plane. I know you haven't gotten to the z-plane in math, but obviously most things in the real world are 3-dimensional, so we do have 3 planes that the p orbital is in. All right, energy level 3 does contain S, P, and D. Okay, we'll talk about how many they have in just a little bit. D does have 5 orbitals, so they're gaining every larger sublevel or subshell. Okay, you absolutely do not have to know what these look like, but they do get more complicated, and you should know that as we go up. So S is a sphere. P is just like 2 of these little lobe pieces. D kind of look like a 4-leaf clover. Most of them do. And then F is even more complicated. Okay, they're not going to show us F. The first thing you need to really write down is that electron configuration. That shows us the occupation of orbitals by electrons for a particular atom. So it's showing us kind of like a street address for electrons. Okay, then I'm going to write kind of similar to this. So I'm going to write a different one. I'm going to write 2p4 Hopefully you saw this in the Edpuzzle. So here, this is the energy level, which is the row most of the time. Okay, what row we're on the periodic table. On the left side of your periodic table, it's got that 1 through 7. That is what we're talking about when I say row. P, or the letter, this is our sublevel. I know it says orbital down there on this slide. Orbitals are different. We'll talk about those in a little bit. The letter is this sublevel, so what section it's in or what block. So I'm going to put block here because you should have denoted those blocks on your periodic table already. All right, and lastly, we have the exponent. The exponent is the number of electrons in that block. And it's the number into the block. So at this point, we need to look at our periodic table. We are on row 2 in section P. So P starts with boron, element 5, and goes to neon. So that's where we're at. So you start at boron and you count 1, 2, 3, 4. So the element that is 2p4 is oxygen. Okay, because we just count into that block. While we're here, I know there's a lot going on this slide. I want you to write S holds 2, P holds 6. These are electrons, by the way. D holds 10. And F holds 14 electrons. Okay, if you go ahead and count across each block, that is how many in that block there are, how many elements. So that's useful to know. Again, remember you can pause this video at any time, but I'm going to keep going. All right, then we've got our orbital diagram. Remember that's a picture representation of our electron configuration. So it gives similar electrons, but it shows arrows in a box instead of just letters and numbers. The orbital diagram is the picture representation of electron configuration. I will ask you to do these along with electron configuration on your quiz or test. You will have to write them out. I don't care which one you do first, you can choose. Okay, there are the rules that we talked about in the POGIL. We're going to talk about them in just a minute. So the direction is called spin, electron spin, and Pauli exclusion is the first rule, so you absolutely need to make sure you have that down. The Pauli exclusion principle tells us that orbitals can hold no more than 2 electrons, and they must have opposing spin. So the orbital is the box. Y'all, when I start drawing these orbital diagrams, though, boxes kind of take a while to draw, so I'm going to draw lines. So one line, which is an orbital, can hold 2 electrons. They must have opposite spin. This is the only one that cannot be broken if it is in the excited state. All the other ones, we can move them around, but they cannot go different directions. That's not an excited state. It's just wrong. All right, this is saying that 4s does come before 3d. They did talk about that in the Edpuzzle. We'll go through that more in a few minutes. So this is the order, so we kind of go up and over, and that's kind of how they go. I know it's not pretty. Again, I'll talk about it, how it works, once we see a periodic table, okay? But see, they are drawing lines. I will draw lines across a piece of paper and just label them because this takes up a lot of space if you draw it vertically. All right, so we know that helium has 2. We know that helium's on row 1, so it's 1s2. Then we go to the next row. Lithium has 3 electrons, so we've got 1s2, 2s1. Again, you've seen these smaller ones before. We'll go through some larger ones in a minute. Hund's rule is next. Remember, this is the bus seat rule. When you're filling the orbitals of equal energy, like P or D or S, because S only has 2 spots, You fill the electrons singly first. And I know that's kind of a weird word, but they go in bus seats. So there are 3 bus seats on the P block. They want to sit alone before they pair. They do have to have parallel spins. They do need to go up first. I know that is not written, but that is how we write them. They go up, 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 and then we pair. So carbon, this is wrong. It's not up, down. It's up, up for 2p. All right, this is the diagonal rule. This is just the order they go in. I know you saw this image on the Edpuzzle. Okay, so you need to follow the Pauli exclusion principle and Hund's rule. The next rule is Aufbau. It should be coming later. If it doesn't, I'll make sure to review it. Okay, I see no Aufbau. Lovely. Okay, so Aufbau. This is the third rule. Electrons fill lowest energy level before moving on, before going to next one. So this is where that diagonal rule comes in, 1s and then 2s and then 2p. You do just kind of go across the periodic table, which is very useful. Okay, electrons fill the lowest energy level and the sublevels before they move on to the next energy level. And let me go back. So it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6p, 4f, 5d, 6p, 7s, 5f, 6d. Again, all of this will make sense, but if you want to write this down, you're more than welcome to, but you do not have to if you can just follow them along on the periodic table. This is Aufbau's principle. They fill 1s before they go to 2s, 2p, then 3s. So I'm going to write Aufbau here too, just so you know. Aufbau's principle. All right, so here's nitrogen, oxygen, fluorine, and neon. Again, you saw most of these on the Pogel. So let's do magnesium. Magnesium was also on the Pogel, but we're going to go ahead and do it. So magnesium we know has 12 electrons. If you want, you can do the end first, but I will tell you, we always start with 1s. So we do 1s2, that's 2 electrons. Then we go to the next row, 2s2, and we just keep going across like you would read a book. After 2s2 is 2p6. So this is neon. We did see neon on the Pogel. Then we go into row 3, and magnesium is 2 into row 3, which is 3s2. That's where we stop. That's it. As far as the rest of them go, you do fill those initial ones up until you get to that last spot. So you could also do it this way. We know sulfur has 16. This was also on the Pogel. I know that sulfur is in row 3. It's in the P block, and if you count it, it is 1, 2, 3, 4 electrons in. So you can start by writing the end, and then you can just fill the rest in, because the rest of them are going to be full. So remember, S holds 2, P holds 6, until you get to that block where that specific element is. All right, I'm going to do gallium now. I wish it would show me the periodic table where it goes. I will tell you, so let's go ahead and find scandium on your periodic table. It's just after calcium, it's number 21. So scandium, in its box, I want you to write 3D. That is 3D1. I know it is on row 4. D is a really big energy level, so it drops down 1. So that means Y is 4D1. Okay. As far as 5D and 6D go, we'll get to those when we see a periodic table, okay? So gallium is in row 4. And it's in the P block, and it is the first element. All right, so again, we're going to go from the beginning. I've got 1s2, 2s2, 2p6, 3s2, 3p6. Okay, then we have 4s2 after 3p6. Remember, after 4s, this is Aufbau's rule, it is 3d. And if you go back to how many d holds 10. Again, though, you could just count across starting at scandium and go to zinc, and there are 10 electrons there. Okay, there will be plenty of time to ask questions later. If you need more practice, you can try those 3. Okay. We'll go through these shortcuts in a little bit. All right, we are going to go ahead and do ions. So remember, ions either gain or lose electrons. Aluminum 3 plus loses 3 electrons. When it does that, it looks like neon because it had aluminum, it lost 3, it goes to magnesium, sodium, and then neon. So this is called isoelectric. This means looks like according to electrons. Isoelectric with neon. So that means according to its electrons, it looks just like neon. So I'm just going to write the electron configuration for neon. That's it. That's our answer. Okay. For chlorine minus, that's isoelectric with argon. Okay, so we just write argon's electron configuration. Okay, oxygen 2 minus looks like neon, so it's the same as aluminum 3 plus. So this is not a big deal. It does get a little bit harder when we get into the D block, but we'll talk about that later, okay? All right, so this is the shortcut. It is called the noble gas configuration. Okay, this says noble gas core notation. I normally call it noble gas configuration. It's because we use the last noble gas that was present. So in this case, we're looking at sodium. So all of this gets us to the noble gas, the 2p6. So I go to sodium on the periodic table. I go up a row and to the end. That gives me neon. So then neon goes in brackets. Brackets, not parentheses. Brackets have right angles. And then we just start at the next row, which is sodium 3s1. That's it. It's much faster, especially for very large elements. Okay, valence electrons, remember, are the outermost shell. I know we've talked about valence electrons, but now they're kind of coming to light with electron configuration. So that means it'll have the highest coefficient to be considered a valence electron. Also, you need to make note, valence electrons are S and P electrons only. Okay, electrons that are not in the outermost shell are called core electrons, which should make sense. Everything that's not a valence electron is considered a core electron. So here, silicon is in energy level 3, 3p2. So everything that's 3 coefficient is considered a valence electron, and all the other ones are core. So if it's got 4 valence electrons and 14 total, 10 of them are core electrons. We're looking here. This is where things get kind of crazy because remember, D is not a valence electron, only S and P. Also notice D is a lower coefficient, so it's not considered a valence electron. So here selenium is on row 4. D are not valence electrons. So if you just want to cover up that D, we've got 6 total valence electrons. Everything else is core. Okay, there is an easier way to see. These numbers also tell you the valence electrons. Generally, the number in front of the A or the number in front of the B on the periodic table, that's like the easy way to do it. It's not always quite accurate, especially in the transition metals, but on the main group elements, it's absolutely correct. All right, so here is that configuration chart. Again, I told you scandium was 3D, yttrium is 4D. Okay, lanthanum on your periodic table, I believe, is down low. I just need you to know that lutetium is 5D1 and lawrencium is 6D1. And see, this is where things get kind of crazy. Okay, so I would consider lanthanum 6s2, 4f, because it's really down below 1, and this one is 5f1. And then lutetium is 5d1 and 6d1. So this is 3d and 4d. F does come before D, because if we split the periodic table like we did in your project, it did come before the D block. Also, it's important to note that the end block, lutetium, I don't know where it's at right now on your periodic table because I don't have one of those in front of me. But just know lutetium is 5D1, lawrencium is 6D1. We'll go from there. All right. Number of valence electrons, we already talked about that. The rho number is the N value, the principal quantum number. Transition metals don't follow electrons configurations exactly. There are some exceptions. Okay, the reason is because if all the electrons can be spread out into their own orbitals or their own space, remember the bus seats, it is more stable than when they have to share some. So like 4s1 3d5 is common. This is really normally, we would write it as 4s2 3d4, but in reality, one of these jumps up to 3d so everybody can have their own space. But remember, these transition elements don't follow the general rule. I will not be testing exceptions. If you come across an exception on mastering, let me know and I'll give you those fraction of a point back because you know it's got a multiple part. Okay. So here it's just showing you how to do it. Remember, this is 3D1, 4D1, 4F1, 5F1, 5D1, 6D1. These go here. Okay. All right. So you can write them for any element on the periodic table. We'll write bigger ones later. Remember, the ions, just look at what it looks like and where it should be. And all chemical properties, pretty much of elements, are determined by their valence electrons, and that's why they behave the way they do. So we know noble gases have 8 valence electrons except helium. Y'all remember helium only has 2 electrons total, so it can only have 2 valence electrons. But the point is, all of these are full for their energy level. So that's why we say they're non-reactive or they're inert. Alkali metals are group 1. Remember, we'd already talked about these. They are the most reactive metals, and they have a +1 charge, which again, already talked about these. But this 1 valence electron, they're going to want to lose them and give them to a nonmetal. That's why they are the most reactive. Alkaline earth metals, or group 2, have 2 valence electrons, so they have a +2 charge. They're going to lose 2 electrons ideally and give them to that nonmetal. The last main group one that has a name are the halogens, or group 7A. They will gain 1 electron because they only need 1 more to get to that full shell here. And so they are the most reactive nonmetals. Here are their charges. We've already dealt with charges. This is not new. All right, writing an orbital diagram for silicon. I would say do the electron configuration first. So silicon is 3p2 because it is 2. It's right after aluminum. So then we fill it in. 1s2, 2s2, 2p6, 3s2, and then we have 3p2. Y'all, this is how I draw my lines. So 1s, 2s. Remember I told you I don't go up and down just because it takes a lot of space. 3s. I will tell you, and this is something students often miss, you do have to draw all the orbitals or lines that are available, whether you have them or not. Okay, so I know 1s has 2, I go up, down. 2s has 2, I go up, down. According to Hund's rule, for P, they need to go up, 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 and then you pair them down, down, down. They are full, but it's good practice to go up, up, up first, so you don't mess that up later. Okay, 3s is full. 3p, there are 2. They go up, up. That is how we draw them. That is silicon. Okay, let's do another one. Argon. Argon is element 18. Y'all, if you do not have to do the electron configuration, that's fine for this. But, so argon's a noble gas. We know it's full. So I do 1s, 2s, 2p, 3s, 3p. 1s, 2s, 2p, 3s, 3p. Y'all, please do not put commas in these. Sometimes students like to put commas. I don't really know why. Don't forget Hund's rule says they're single before they pair. The conventional way is to draw up first. That one is full. We're done. There's obviously going to be questions on mastering where you're kind of dragging and dropping. All right, now for selenium, which we just did. Nope, we didn't do selenium. We did silicon. All right, so it wants the electron configuration. It wants valence electrons and core electrons. So selenium. Selenium is 4p4. I'm going to write that down here. Again, just count over. We go back. We start at the beginning. 1s2, 2s2, 2p6, 3s2, 3p6. Y'all, you should be okay up to 3p6. After 3p6 is 4s2, but then don't forget 3d10. Okay, 3d is before 4p. Remember, highest coefficient, these are our valence electrons. So that's 6 valence electrons. Everything else is core. And you know what, that points to core electrons, so I'm just going to leave it. So selenium has 34 total. So there are 28 core and 6 valence. Okay. It's not too bad. You just have to be able to identify what we're talking about. All right, chlorine. I'm just going to go with the 7A. Chlorine has 7 valence electrons and 10 core electrons. There they are. You can see them. All right, arsenic. Write the electron configuration for arsenic. Arsenic is AS. That is 4p3. Make sure you fill in 3d. They are using the noble gas configuration. I'll use that more on larger ones. So 10 is very large. Notice it is element 50. It is in row 5. So this is where I'm going to use my electron configuration. So I'm going to take 10. I'm going to go up a row and to the end. That is krypton, Kr. That means all of row 4 is denoted by me writing that Kr in brackets. So I'm going to start on row 5. 5s2, 40, 10, and then 10 is 1, 2 into 5p. That is the easiest way to write them, but you can only do that when I specify that on like a test or on mastering. I do think on mastering though, it takes it most of the time this way, but on the test, I will ask for the full version and the noble gas configuration. All right, that's where we're stopping today. So y'all have a great day.